This is the data analysis of adding vectors, and I found these 4 websites. So I'm going to show you how to use them, and it's your preference which one of the 4 you want to use. I'm going to use my example here. So I have these 3.5 newtons, 2.3 newtons, and 1.7 newtons at these angles, 180, 270, and 0 degrees. And when I use the applet, and you will see that, I would come up, it would calculate for me 2.9 newtons at an angle of 232 degrees. Now, when I measured it in the video, the counterforce, I came up with 2.7 newtons. That matches the applet computation pretty nicely, 2.9 newtons. Of course, this is a measurement, so it is odd to be off just a little bit. Then there it is. And then I measured in the video 55 degrees. And that seems to be a lot off, but it's not. It's actually right on, because the 3 forces that I have over here, they're pulling in one direction at an angle of 232 degrees. But when I apply the counterforce, that of course has to pull in the opposite direction, so at 55 degrees. So 55 degrees is almost opposite of 232 degrees, 180 degrees away. So anyway, that's where that was coming from. So let's look at these different websites here. All right, going to start with this one. This is the hyperphysics one, and I already put the angles in, so I don't have to type too much here and take a time away in this recording here. So 3.5, 2.3. Notice it recalculates every single time. At the end, I have to click somewhere else. It doesn't have an enter button in order for me to actually calculate, and there it is, 2.9 newtons rounded, and here around it 232 degrees, just as I showed you for my example on the lab sheet. Okay, here is another one. So this has the strange name of 1728.org, vectors. 180, 270, 0. I already plugged in the angle. So here's 3.5 newtons, 2.3 newtons, and let's see, 1.7 newtons. There it is. This time I do click calculate, and here it says rounded 2.9 newtons at an angle of 232 degrees. So it calculates that as well. This one here is the FET, even though I do like PHET, but this is rather clunky, so I cannot actually enter these numbers up here. I have to do this one here, so for example there, and then I can't even do it 3.5. See, 4 or 3, something like that. I would have to actually draw it all the way out to 35. I'm going to skip this one here. Let's do the other one. Let's do the Desmos. This one does work, by the way. It's just a little more clunky. All right, so here's the Desmos, and I have red, green, blue, and orange ones. In this case, I only have 3 vectors, so I don't need the orange one. I'm going to start with the red one. So this is 180 degrees. There's 180. By the way, this one here that moves, that's actually the resultant force. And then here, this one I can enter, so 3.5. There it is. Negative simply means it points to the left. So there it is, there, right there. And then the other one says, let's see, 270, and this one is the green one. And that one would say 2.3, so I'm going to change this one here to 2.3. There we go, and then there's a blue one that says 0 degrees. There we go. Actually, the blue one is here. There we go. And I have it already at 0 degrees now, and then it's going to say 1.7 newtons. Whoa, okay, that was a little bit too much. There we go. 1.7, there we go. Click somewhere else, and here it is. This one here actually says in the instructions to estimate the angle, and if this is 210 degrees, 240, then this must be 225. So this one here looks kind of like around 230, 232 degrees. So that would make sense. It does calculate the total force here, which again is 2.9 newtons, as it should be. And these are the various applets you can use in order to come up with the theoretical result for these forces. So this is the analysis for the what I call the human forces, or these people pulling on these spring scales on that strong metal washer. And this is what they measured in that example: 95 newtons, 30, 70, 29 newtons at angles of 0, 90, 180, and 240 degrees. The applet, as we will see here soon, calculates 12 newtons at some kind of angle. However, that angle really doesn't make sense because these 12 newtons here should be actually close to 0, and a 0 Newton vector wouldn't have any direction, so we disregard the angle. I claim that 12 newtons is close enough to 0. Doesn't look like it, right? But if you compare it to the 95 over here or the 70 here, it's rather small. In fact, when you add up all these forces here, 29 and 70 and 30 and 95, which I do in this kind of footnote here, I come up with a total of 224, I believe, which I divide into 12, and that gives me the error of 0.05 or 5%. That's where this one is coming from. This one is a relict here. That shouldn't be there. But I guess if you do set up E, you will come up apparently with a 1% error, so even better than my example. Okay, so let's look at the applets, the various ones. So here's the hyperphysics one, and again, I put in the degrees like I did earlier, but here are the numbers: 95, 30, 70, and 29. And again, I have to click somewhere, and here it is. There's that rounded 12 newtons. And again, we don't need the angle because everything is in equilibrium. It's not moving anywhere. All right, here is the other one. So again, I'm going to put these in here: 95, 30, 70, and 29. Calculate, and there it is again, 12 newtons rounded. Again, I'm going to skip the PHET. That's even more clunky for this one here because I cannot even get 95 on here. All right, so here is the Desmos. And I'm going to do the red one here at 0 degrees. And then technically, okay, let's do it a little bit closer, 0 degrees. I'm trying to get this one here down to 0. So it has no vertical component. But when I type in here the 95 for that, I get way off the screen, right? And so I actually have to zoom out. There's a negative button here to zoom out with. Not too much because I still need to grab the others. I can also do that with my little wheel on the mouse to zoom in or out. Let's see, the next one I have is the green one. So this one here is at 90 degrees. If you go again, this one here should go to 0, and then this one here I'm just going to put in manually 30, and then I'm going to grab the blue one at 180 degrees, and that should be 70. There we go. And then I grab the orange one here, right here, and that should be 240 degrees. Let's see. Oh, there it is. There's the 240 degrees. Hopefully. Ooh, and that actually produces a problem because this one right here should be 29, and so unfortunately I have to try something here. I have to manually change this one here, so that becomes a little clunky now. I'll see what I'm doing here. So now I can actually do this here, and down here there's 29. I'm really close. Come on. I was really close there. That's good enough, right? And then here is my resultant vector, and if I scroll all the way up, so again, this one here is around a 29, and we can see that this is an angle of 240 degrees. So as I go up here, here's the resultant. There it is again, 12 newtons, just like the others. I know this was a little bit clunky, especially for the one at the odd angle. I have to adjust that carefully, but we can see that this here is the resultant at 12 newtons, and it's relatively small compared to the others. That's why I like doing this one here with the Desmos, because it shows it better than the others. The others are just computations, but this one is actually graphically. All right, that's the analysis for these, what I call human forces or people, something like that.